You're on.
Hello, I'm Brad Defelice, and my project is the CowCatcher 3000. It's a solar battery-powered electric fence charger with wireless remote monitoring. So just fence chargers in general, they're used to manage livestock in outdoor pasture areas. They're actually more of a psychological barrier than a physical one. It trains the animal to avoid the fence because it gets a shock every time it touches it, so it does not want to touch the fence anymore. So it creates a negative conditioning response. This is just a chart that says recommended voltages for different animals. For my project, I focused on cows, which are 2,000 to 3,000 volts, horses 2,000 to 3,000 volts, and pigs that are 2,000 plus volts. So my fence charger only puts out between 2,000 and 3,000 volts. My interest is that I've raised pigs before. I've used an electric fence charger, but mine was more of a plug-in model. So I wanted to make something that would be more, I guess, off the grid, using more of a battery and solar sources. At the end of the project, I'm going to give this to my friends, and they're going to use it to manage their livestock and the land that they purchased. Some of the features of the fence charger are that it accepts multiple voltage sources, so you can hook it up to a battery, you can hook it up to a solar panel. The fence charger circuit is included in it. It has a built-in microprocessor, the remote monitoring station that would be placed somewhere away from the actual fence charger, and it's got easy setup. Some of the specs are that it actually can handle voltages between, that's a typo, but that's supposed to be 12 to 20 volts and 12 volt battery. It also can, it's also got a 60 hertz charge rate, so every 60 hertz it's going to keep pulsing the fence. It has a 1 mile fence capacity, and it can remote monitor within 100 feet of the actual unit. So this is my system diagram here. Either solar or the battery will give the fence charger its power, or both. You can actually hook up both. The fence charger has a built-in microprocessor that then transmit a wireless signal through an antenna to a receiver that would be located possibly in a house or maybe in another barn somewhere. That will receive the signal and then give you a green light or a red light. The green light would tell you that the fence is operating correctly and there's no load on the fence at the moment. A red light would tell you that there's possibly a load on the fence or that the unit's not working at all and it's not receiving a signal. The receiver will also have a built-in microprocessor so it can interpret the signal coming from the other microprocessor. And then the fence charger just kind of hooks up to whatever electric fence you have, whether it be 2-line, 3-line, something like that. So, can you go back one? This section right here that I kind of outlined in red is actually what I actually built in the system diagram. If we go to the next slide, I kind of blew it up a little bit so you can see what it actually is. So this is what I actually built. Right here is the charge circuit. This is where you would hook up the ignition coil that gives you the high voltage. Here's where you would hook up the battery or the panel for your power coming in. Right here is the KL25Z board that the transmitter board that I built plugs onto, and this is the transmitter right here, and this whole thing is the antenna. And then on the receiver side, these are the status LEDs that tell you good or bad. This is the receiver right here, another battery connection terminal, so you can give this power, and the KL25Z board that it plugs onto. So in my fence charger schematic, I have a couple main points here. This is a voltage regulator that's going to take the voltage from the battery and reduce it down to 5 volts that the KL25Z can handle, and also the transmitter will get that power too. I created jumpers here to break up my grounds because I have a high amperage side over here for the actual fence charger circuit that can draw anywhere from roughly 3.5 amps. But everything else in my circuit draws only milliamps. I have a 6 milliamp drop here and a 21 milliamp drop over here, so I I broke up the ground so I could actually make this trace here a lot thicker than the other traces in the other part of the circuit, and I did the same thing with the power supply so I could break that up too. So the trace on this is going to look significantly bigger than the trace on this and the trace on this, and you can see that in the next slide. When you see my board layout, this actually right here is the high current side. It's got the thicker traces, and then the medium current, I guess you would call it, the 21 milliamps is the thicker traces here, and then the 6 milliamp is the really thin traces there. If we go back to the schematic, so I have the voltage regulator here, we have a power MOSFET here, 2 regular transistors, NPN transistors, and this is my sampling resistors right here. So I actually take the sample of the voltage coming off of these 2 resistors on the low voltage, high current side of the fence charger circuit, and it goes into the KL25Z microprocessor. And then, I guess that's pretty much it for that slide. Go one more. And then the transmitter and receiver aren't quite as intricate as the fence charger schematic, so I didn't include the board layout, but basically over here on this side, if you were to draw a fake line there, that I guess I should have, you would see that this is just the transmitter pin layouts, and then it has a little status indicator light here to just tell you it's working, so if somebody went out to the actual unit, they could see if it was getting power or not. And then this is the receiver side, and that just plugs onto the KL25Z board also, and it has 2 of the status indicator lights here, and the battery connection is up here. Okay, so some of the waveform stuff. So this is actually off the sampling resistor. This is where there's no load on the fence, and I found out that this voltage here stays the same whether there's a load or not, so I had to figure out a different way of how to determine whether there's a load. So I found out that the actual timing of the charge here changes when there's a load and no load. So when there's no load, it takes about 10 milliseconds to reach up to the V peak of 182 millivolts. And on the next slide, it shows with a load, and the time actually doubles here. So it goes from 10 milliseconds to 20 milliseconds to get all the way up to the peak charge there. So this is how I will actually determine, or how I do actually determine whether there's a load or not on the fence. This sampling resistor data goes into the KL25Z board, and the microprocessor uses a comparator, and it determines, basically, it starts a timer from when the charge is drawn, and then when it reaches this peak here, it stops the timer, and it basically counts the seconds, or milliseconds, and determines whether there's a load or not through the software. And if there is a load, it basically determines how long the load has been on the fence, if it's been a minute or 2, and then it gives the user a status indicator light, will come on saying there's a load on the fence, go check it. Because it could be an animal caught, or it could just be a branch or something on the fence itself. So going into the transmitter side of things on the project, I had to determine how to transfer data from the wireless transmitter to the receiver, and luckily the KL25Z, the microprocessor, has a built-in UART protocol, so it has its own protocol on how to do highs and lows, to basically create binary numbers. So this is just an example when I was testing it on the bench. The blue right here is the transmitter, and the yellow is the receiver. And it's kind of interesting, they're not exactly the same, so I could get errors in my receiving. It's weird because the fall edge usually lines up perfect. It's the rising edge that gets skewed a little bit. So to overcome this problem here, I basically did it in software, and if you look at this board here, basically it created 2 different codes. One's good, one's bad. So if it sends a 60, it's good. If it sends a 195, it's bad. But to compensate for the errors, I did a couple little examples here that, like, if it shows, if it doesn't quite catch the rise, or it does the rise early, it'd be a 124. If it does the fall late, it'd be a 62. So I did a range of numbers. So if it's anywhere between 0 to 65, I call that a good code. And if it's anywhere from 451 to basically, I went all the way down to I think 100, it would be a bad code. So to overcome this problem, I did it in code by basically just giving it a range of numbers. And as you can see, it's pretty close, so it could be skewed a little bit either way. But it kind of does the point of what I was looking to do. So some of the ethical and environmental issues with this would be, it's less harmful for the animal. There's no barbed wire for them to get tangled in and cut and physically harmed. It creates a conditioned behavior instead of I guess, just running into the fence and keep going. You can be more energy independent because it can run on solar or battery or both. So you're not using any of that grid power that's usually run by fossil fuels, except for Vermont, we're a little bit more green. So yeah, and are there any questions?
Back on your system diagram slide, did you build in a battery charger to charge the battery from the solar as well? Is that happening?
No, I didn't do that. I was figuring that people could just get, because I only recommend this for an actual, like a lead acid battery. So I don't recommend it for any of the more fancy batteries. So I figured that people would just buy a solar panel, and usually they come with a diode built into them. So I was figuring just hook that right into the battery. Any other questions?
All set, thank you.